Today we're going to continue our discussion on properties of sound, define Doppler shift and identify some applications, relate physical properties of sound waves to perceived pitch and loudness, and describe the frequency ratio identified with octaves, thirds, fourths, and fifths. So if you look at your bell ringer here, how long will it take the sound of the starter's pistol to reach the coach 100 meters away if the temperature is 45 degrees? Go ahead and pause the video and try that real quick, and I'll show you the answer. We know velocity is distance over time, so time is distance divided by velocity. My distance is 100 meters. I just need to divide that by the speed of sound, which is normally at 20 degrees Celsius, it's 343 meters per second. But we're at 45 degrees. So there's a difference of 25 Celsius degrees, and the speed we know changes 0.6 meters per second per Celsius degree. So if you take 0.6 times 25, you end up with 15 meters per second. So the speed of sound is actually 15 meters per second greater than at 20 degrees. So you have to add these two together, and our new speed of sound is 358 meters per second at 45 degrees Celsius. We take our 100 divided by 358 meters per second, and when you do that, 100 divided by 358 will give you 0.279 seconds. You'll see the smoke from the starter's pistol initially or immediately, because speed of light is almost instantaneous, 3 times 10 meters per second. You will hear it 0.28 seconds later. So if you're going by sound, their times will be actually a little faster than if you go by when you see the light. Well, let's get to our notes here. 15.1 continued. This will finish up section 15.1. The Doppler shift is the apparent change in frequency when a sound source moves. We know that the frequency comes from the object. Something is emitting a sound, and that object is making or creating a certain pitch, and that really doesn't change. However, it appears to change when the sound source moves. And if the sound or the object is moving toward a detector, the apparent frequency, and that's what this thing means, right here it is a little hyphen F. F prime is your apparent frequency is higher going toward the sound, and it's lower going away from the sound. Or if the sound is moving towards the detector, it is higher and lower going away from. I'm going to show you a little video clip here, or animation, that kind of explains or shows this. You've got a bee emitting out some type of sound, and there's a microphone over here. Notice when the bee comes towards the microphone, the waves get compressed, therefore higher frequency. As he goes away, they're compressed behind him and spread out toward the microphone. That would be lower pitch. Now he's going toward, it would be a higher pitch, because you have more compressed waves, higher frequency, and so on and so forth. You can see the website if you want to just play around with that yourself. Since the velocity is unchanged, if the wavelength decreases, the frequency would have to increase. You know, the speed of sound is a constant in a given medium. So if you change your wavelength, it has to be at the expense of the frequency. We know velocity is wavelength times frequency. So if the wavelength goes down, the frequency would have to go up in order for the speed to be a constant. And like I mentioned, it also works if the detector moves and the sound is stationary. Now this occurs in all types of wave motion, both mechanical waves and electromagnetic waves. This is how bats, which really can't see, can detect there are objects around. A bat flies, sends out a frequency, and if the reflected pitch is higher, then the object must be flying towards him. If it's lower, the object is flying away from him because it's stretching the wavelengths. If you have a large object, what's going to happen to the reflection? Well, it's going to be a greater reflection than if you had a smaller object. This is kind of how radar works as well. You can see if ships are going towards or away based on what's happening to the reflected wave and this Doppler shift. Now there is an equation to calculate this apparent frequency. This F stands for the original frequency. So that would be just the frequency of the sound that's being emitted. V is the velocity of sound, which is typically 343 if you're at 20 degrees. V sub D is the velocity of the detector we have written right here. And V sub S is the velocity of the sound source. I'm sorry. So you have the thing producing the sound, the source, sound source, and you have the object detecting the sound. If the detector, the velocity of the detector, if you're going toward the source, then you put a positive value in for the detector. And the sound, if it's going toward the detector, would put in a positive value as well. So let's try an example here real quick. Here's my equation. Apparent frequency is the frequency times V plus V sub D over V minus V sub S. And let's pretend I've got an object, maybe a car, moving at 35 meters per second. And the horn has a frequency of 205 hertz. And a person is stationary, listening to the car come towards it. What is the pitch that person would hear? Well, the original frequency was 205 hertz. We're going to assume 20 degrees Celsius, so your speed of sound is 343. What's the velocity of the detector? Well, the detector is the person, and they are stationary. So this is a 0 there. And our source, the source of the sound, the car, is moving, and it's moving toward the detector. So if the source is moving toward the detector, you need to put a positive value in for V sub S. So this is just a positive, V sub S is a positive 35, which in effect means you're going to subtract those numbers. So you notice you have 205 times 343 divided by 308. And if you multiply those together, 305 times 343 divided by 308, you get 340 hertz. Notice the pitch right here is a lot higher than the original frequency because those waves got compressed toward the detector. If the sound source was stationary, you'd put a 0 in the bottom here, And if the detector was running towards the car, you put in the speed of him running right there, and it would also alter the apparent frequency. So, pitch and loudness. A lot of you are in music. You understand pitch and loudness. The pitch is actually the frequency of the wave. The higher the frequency, the higher the pitch. Middle C versus a high C. High C has a higher pitch, therefore higher frequency. Loudness is really just the amplitude of the pressure variations of your wave. So if you have a more compression, more tightly compressed, it's going to be louder, because compressions are like your amplitude for sound waves. If it's compressed more, it's louder. If there's less compression, it's going to be a softer wave. Now for the test, I'll expect you to know, one of the objectives was to know the frequency ratios for these different chords. An octave would be going from one note to the same note 8 steps higher. So a C to a high C, the frequency ratio is 2 to 1. If middle C is 256, an octave above that would be twice as big, 512. A C to an E is a major third higher. These are the frequencies for Cs. So if you want to go to an E, and your C was 256, you need to take that times 5/4. And if you double check, hoping this is right, 256 times 5/4, you get 320. A major fourth. If you have a middle C, which is 256, and you take that times 4/3, you end up getting 341 for your frequency. And a major fifth, if you take again the middle C and take that times 3/2, you get 384. So the frequency ratio, 384 to 256, will be 3 to 2. And that's going from a C to a G, 5 steps up. Kind of interesting how they happen to be whole number ratios. 5 to 4 for a third, 4 to 3 for a fourth, 3 to 2 for a fifth, 2 to 1 for an octave, or 8 steps up. And you will have to know those ratios. Last thing, sound level. This is measured in units of decibels. And it's kind of interesting because science is always precise. We define sound level as the pressure of the most faintly heard sound, which is interesting because that actually can vary based on different people. They have different sounds they can hear. Look, 0 decibels has a pressure of 2 times 10 to the negative 5th newtons per square meter. And every 10 times increase in the pressure results in 20 decibel increase. So if you take this times 10, this original amount, pressure, times 10, you get 2 times 10 to the negative 4th, and that corresponds to a 20 decibel increase. If you do that again, 10 more times, your pressure is 2 times 10 to the negative 3rd, and that again will add to a 20 decibel increase. So notice it's not related. Every time your pressure goes 10 times larger, the sound level increases by 20. to give you an idea, 10 decibels is barely audible. 50 decibels would be a moderate, kind of like normal noise in a classroom. 100 decibels would be a fire truck siren type of thing. And you really want to keep your decibels under 100. Loudness is not directly proportional to the pressure variations. For instance, if you increase 10 decibels in sound, to us, we perceive that as sounding about twice as loud. So if you increase another 10, that would be another twice as loud. It'd be 4 times as loud, but really it's 10 times as much in terms of pressure variation. So it's really not directly related. If you look in your chart on figure 15.3 on page 353, they give you these different sound levels that I had mentioned. So if you wore earplugs that would block out 40 decibels and you were driving the fire truck, obviously it's going to reduce that from 100 down to a feeling like about 60. And hopefully that helps protect your ears and such. That ends section 15.1.